to settle this issue because it troubled me at the time. So we were looking at this expression, which was looking at the power series 1 over k to the p. And I said it converges if and only if this integral. This is basically just the integral test. If that integral is finite, then the series converges. And we're able to evaluate the integral, which looks like this. Right? Just add 1 to the power, and then divide by that number, and evaluate between infinity and 1. And so we evaluated, and we got 1 over p minus 1. And here's where the issue came in. I looked at that and said, well, clearly when p is 1, this is bad. It'll be non-finite. But when p is smaller than 1, this will be fine. It'll just be a negative number. It's still finite. And the conclusion of the integral test seems to me it would say no problem. Then you've got a convergent series. But the problem is we know p series only converge for p greater than or equal to 1. So what went wrong? And it took me a second after class ended to sort this out, but it was right here, this 0. You see, we looked at the upper limit and we said, well, if x is large and this power on x is, let's see, we were talking about p bigger than 1, so we would have a negative power on x. So x is some giant negative power, that's like 1 over x to a positive power, and that's going to approach 0 when x is infinite. But in the other circumstance, where p is less than 1, we would end up with a positive exponent on x. And instead of having 0 at the upper limit when x is infinite, we'd actually have infinity right there. So this thing blows up for different reasons, right? When p is less than 1, it blows up because the upper limit is infinite. When p is equal to 1, it blows up because the denominator there is 0. But when p is greater than 1, it's all golden. You get 0 at the upper limit, and then so you'll be just subtracting the 1 over 1 minus p. And then switch the order and take care of the minus sign, you get 1 over p minus 1. Yeah, so this basically the evaluation at the upper limit only works in the case we know is actually the situation. The power series converges when p is greater than 1. So, hi. Today I'm going to give you a lecture mostly about the ratio test and the root test, two very useful tests, to tell whether a series, gotta say that right, a series is convergent or divergent. But there's one little thing I wanted to finish out in the section on alternating series that is a nice estimator for how much error is there in a partial sum. That is, if you use one of the partial sums as an estimate for the limiting value of the sum, how bad is it? It's great to have estimates of how accurate your approximations are, and this is a scenario where we do have an excellent estimator. So the Desmos graph here is something I just kind of cooked up, but you can think of this as an infinite sequence. It's a graph that you see has a sort of oscillating character. There's actually quite a lot of physical phenomena that have this sort of behavior. You throw rocks into a pond and watch the ripples spread out. They look like this. They start out large and then they get smaller and smaller, and eventually, the limiting value here is sea level if you're talking about rocks in a pond, or pond level. Anyway, the limit of the sequence, or the series that I'm trying to get out of this thing is the values are the peaks that we're seeing. So the first peak we see has a y-coordinate of 1.05, then 0.973, then 1.01, then 0.9894. Okay, so the reason those are strange looking numbers is that they're sort of cooked up. But I want you to think about the character of something like this. If a sum is gotten by first adding something, then subtracting something, then adding something back in, then subtracting something more, how accurate is one of these things compared to the limiting value? Here you can see the limiting value is y equals 1. I should have just put that in already. Y equals 1, that green line, isn't it? But these values, the maximums along this curve I've got here, oscillate back and forth around 1. And that's because if you were adding an infinite series to get these values, you'd start probably at 0, then you'd add this number a little bit bigger than 1, and then you'd subtract something to get down to here, then you'd be adding something. So how's our error estimate going to proceed? I want us to think about that graph, but now don't do the graph explicitly that's there, but just think about any alternating graph. I'm having a problem getting focus to happen. Come down there. Thank you. All right, so look at a graph where we're just concerned with the y coordinate. Okay, so really we would be plotting, values that approaching some value, the partial sums of the series. That is, the things we're plotting are y equals s sub n, where s sub n is the sum that goes from I equals 0 to n of a sub I. Okay. And I guess I would really be thinking about plotting n comma y here. Oops, n comma y. The x coordinate would be this number, how far do we take the sum, and the y coordinate was what's the value of the sum if we've only got that many terms. So we've got a value when there's a single term, there's a value when there's 2 terms and 3 terms, and so on. But instead of thinking about this in the xy plane, just look at how it looks on the y-axis. It's a sequence of points on the y-axis that start out by going, well, it starts at 0, and then we go up to that value, and then we subtract something, and then we add something, and we quickly see that we get stuck in between two things. So if there is indeed a limiting value, let's call it L, we'd like to know how good is one of these S sub n's as an approximator for L. That is, I want to think about what is the difference between one of the sums and L. And let's do a blown up view of the situation. So here's our L, some horizontal line we're approaching, and maybe that's the value of S sub n. Well, the difference between S sub n and L is this length right in here, because the dashed line is y equals L, right? And S sub n is y equals wherever the value of the nth sum is. So that's the difference I'm referring to, that little bit of height right here. Look where S sub n plus 1, if we took one more term, because this is a series, or we're assuming this is a series that is the sum of an alternating sequence, S sub n plus 1 would be down here, below that. And that is a larger number than the difference between S sub n and L. So that is, I can fill this in with an inequality. There's a bigger number, which is the difference between S sub n and S sub n plus 1. But we know exactly what S sub n minus S sub n plus 1 is, or rather, what its absolute value is. I mean, what is the height of this thing? That's just the n plus first term of the sum. So, well, that n plus first term might be negative, so I do mean the sort of absolute value of it. So this last expression I've written here is equal to the absolute value of a sub n plus 1. got a little too close to the edge of the margin there, so I don't have room for my here. Let's just take it down a line. It's the absolute value of a sub n plus 1, right? Which means something important. It means that the next term in the sequence, or at least its size, will give you an estimator for how good the approximation at level n is. If you want to know what's the error, what's the largest possible error in the nth partial sum as being used as an estimator for the limit, it's just the n plus first term. Now that discussion is incorporated in a theorem from our book about the remainder in alternating series. They've got the same talk that I just gave up here in the intro to this, and they never prove the result, which is fine. I think it's something we can just understand directly. The idea, though, is you're looking at an alternating series with minus 1 to the k plus 1 as, I don't know why they wanted to do that. I guess that makes the first term positive. That's nice, but it could have just been minus 1 to the k. In any case, an alternating series and a sub k now would be a strictly positive thing. The minus 1 to the k is taking care of the alternation, and the a sub k is the positive amount. So you've sort of already taken care of the absolute values. Okay? If you've got the a sub k is strictly positive and you make it alternating with that introduction, then see how the result is set up. Just what I said before, the difference between the nth partial sum and the n plus first partial sum, the absolute value of that, is equal to a sub n plus 1, and that's an upper bound on how far, okay, they used s rather than l, but same idea, that the partial sum is being used as an estimator for the actual sum, and this difference in absolute values tells us how far off we are. It's literally the absolute error in the approximation of s by a partial sum, s sub n. And it's the biggest it could be is the next term in the sequence, a sub n plus 1. So the preliminaries are over. We just finished a couple of things cleaned up from 10.6. 10.7 has some really good stuff in it. These two tests are kind of the meat and potatoes, as it were, of figuring out whether things converge or diverge. And actually the beginning couple of paragraphs here of section 10.7 do a nice job of sort of explaining what's the situation. So up to this point, we've got the alternating series test, which is great, but what if you don't have an alternating series, your host? And we've got the integral test. The integral test is lovely, but if you can't integrate the thing you're after, then it's not gonna fly. So they give an example in here of the summation of 1 over k factorial. The terms of that go to 0 quickly, right? So because k factorial grows so huge, it makes sense that this converges. But can you integrate 1 over x factorial? I think they should have written x factorial myself. But anyway, yeah, you can't. There's no closed form for that integral. So that's a problem. There is also the comparison tests, and those are great, but they're hard to use. It's hard to figure out what to use as the thing to compare your given sequence with, your given series with. The ratio test and the root test are sort of machines. You plug in the series you've got, and you don't need to compare it to somebody else. You don't need to do an integral. You do need to evaluate a limit, which usually ends up being not so bad. Okay, so let's talk about it. The ratio test, here it is. Let a sub k be an infinite series, and let r equal the limit as k goes to infinity of the absolute value of the ratio of ak plus 1 over ak. So I think of this as you're at stage k, you look at the next term, k plus 1th term, and the kth term, you divide, simplify, and then see what the limit of that expression is as you head off towards infinity. That's all. It's not actually that hard to do. We'll do some examples. But what this test tells you is pretty simple. First of all, I would take the last thing first. It says if r is equal to 1, the test is inconclusive. You don't know whether it converges or diverges. Just the test isn't telling you yet. But if R is less than 1, you know it converges. Indeed, it converges absolutely. And that means it converges without the absolute value bars. So, and then if R is greater than 1, you actually definitely know it diverges. So the only place where it doesn't quite tell you the story is that one thin moment when X is 1, or R is 1. Why don't we look at the ratio test for the example that they gave here, the limit, the sum, 1 over k factorial as k goes from 1 to infinity. Like I said, that almost certainly converges, but let's see what the ratio test would tell us. We look at, let's come back to here, right there, the ratio of the next term to the previous. So we're going to look at 1 over k plus 1 factorial divided by 1 over k factorial. And then we'll take the limit as k goes to infinity on that thing. Well, this kind of expression with factorials, it looks hard at first, but in fact it's pretty easy to deal with. Instead of dividing by 1 over something, let's multiply by the reciprocal. And if we multiply by the reciprocal, instead of dividing by the original, we end up with 1 over k plus 1 factorial and times k factorial over 1. All right, and this is best thought of is expanded out. Remember, this is the product from k all the way down to 1. And this is starting at k plus 1 and going all the way down to 1. This k plus 1 factorial includes all the terms that are in k factorial. And then that one extra one, it's k plus 1. Right? So that simplifies. Maybe I should write it out just to make sure everybody's good on this. The numerator has k factorial, so it's k minus 1, k minus 2, and so on, down until we get to 1. And the denominator has k plus 1, and then k minus 1, and right on down until we get to 1. So the k minus 1 through 1 and this k minus 1 through 1, they cancel. Wait, that k and that k is also going to cancel, right? So everything from k down to 1 on the bottom and everything in the top goes away. So we end up with the limit as k goes to infinity of 1 over k plus 1. Which is an easy limit to evaluate. That's 0. Yay. So what does the test tell us? The R is definitely less than 1. This thing for sure converges. That's what the test tells us. So we've just looked at the ratio test in the book. I wanted to explain a little bit the sort of feel behind the ratio test. And before we do that, I need a little bit of new terminology. So suppose you have an infinite sum that has, I'm going to write it out for a while. And then beyond there, there's a sub n plus 1 and more stuff. More, a n plus 2, a n plus 3, etc. This part, this initial n terms, if you add that stuff together, that's known as the nth partial sum. The rest of the stuff that would go from n plus 1 out to infinity, that's called the tail. And I suppose you could say it's the nth tail, right? It's everything from the n plus first term forward. Convergence of a series really has mostly to do with tails. If, in particular, if the tail is not finite, there's no way the series converges. So let me try to say this as a proper if-then sentence. If the nth tail of a series is infinite, then the series diverges. Well, there's a standard trick of logic, which I think I've referred to before, but I'm going to definitely want you to think about it here. If you reverse the direction of an if-then sentence, that is, switch what's the if and what's the then, but also negate the pieces of that if-then sentence, you will get something that's logically the same. So let me do that here. That would be talking about the series not diverging but converging first, and the tail of a series being the opposite of infinite is finite. So let me say that out in words. So if a series converges, if a series converges, its tails must be finite. So what the ratio test is really about is giving us an estimator for the tail of a series. And if your estimate of the tail of the series is that it's finite, then you're going to know that the series converges. And vice versa. If you find out the tails, or some of the tails are infinite, then you know for sure the series does not converge, it diverges. All right, so why does this work? Again, think about the setup I've done above. You've gone way out along the line. You're at some value of n, right? Think of the n as being pretty large, and then the terms from here on out are that tail we're interested in. Well, that tail is well approximated by a geometric series. Writing this out, but let me get to the end of the sentence and then I'll talk about it. Can't write and talk at the same time. The tail is, I should have said well approximated. It actually gets to be remarkably good later, the farther out you go. Why? Because we know that the ratio between a sub n plus 1 and a sub n is approaching r. So you can say, well, look, the tail, do you mind if I write tail, T for tail? The tail is approximately a sub n plus 1 plus the next term down would be that ratio times a sub n plus 1. So whatever r worked out to be times a sub n plus 1. And the one after that, this is a sub n plus 2, well, it's an approximation of it, would look like r times that. So we get r squared times a sub n plus 1. So the tail looks like a sub n plus 1 times the geometric series with common ratio r. And the infinite geometric series, well, if r is less than 1, this is finite. If r is bigger than 1, this is definitely infinite. And if You don't have to have that good of an approximation if this is even somewhat close to the size of the tail of the series, and this one's infinite, then it's pretty clear the tail is too, isn't it? So yeah, that's what's going on behind the ratio test. You're figuring out a way to make the tail of the series look like very close to at least a geometric series, and then asking yourself, well, is that tail going to be a finite number or no? Supposing it's finite, then you've got a finite partial sum plus a tail that's finite. You get a number for the sum. If the tail is infinite, you're hosed. You're going to have some partial sum plus hidden out in the infinity of terms there that make up the tail, there's some other infinity that messes it up. There's an example of using the ratio test, because I think once you've grasped what it says, it helps to put it in practice at least once so that you can really, internalize it. There's example number 1 on page 697, which has 3 parts, A, B, and C. I'm going to look at part B, because I think they're a little fast in the algebraic manipulations in terms of showing the ratio test works here. I encourage you to look at parts A and C on that. I'm trying to think. They only do the one example, so the rest of the examples will be relegated to the homework, I guess. But let me do this example 1, part B. Now the series involved here is kind of an interesting one. The positive part of it looks like k to the k over k factorial. And then there's an alternation in it. Minus 1 to the k power. So all the odd number terms will be negative. Right? And wow, you might say, gee, I don't know, does this even, do you think this converges? Which is bigger, k to the k or k factorial? K to the k has k copies of k. It's k times itself, k times. K factorial has k numbers multiplied together that are starting at k and going down. So might seem like they're about the same size, right? But I just argued to myself that they are the same size, and so maybe this is coming to, well, actually I do know this series converges, so it's gonna definitely be the case that k to the k over k factorial is approaching 0. My brain is broken right now. I can't figure that out, but that's okay. Let's just apply the ratio test. What does the ratio test say we should do? We should look at, call it r is equal to the limit with k going to infinity of the k plus first version divided by the kth. Now that'll be minus 1 to the k plus 1, k plus 1 to the k plus 1, and then divided by 1 over k factorial. Let me just say 1 times 1 over k plus 1 factorial. What's in the bottom is the same thing, but with the k's turned into k's. Yeah, the k's left as k's, that's what I should say. Anyway, minus 1 to the k, k to the k, and 1 over k factorial down here. And actually, let's see, didn't the ratio test say I looked at the absolute value of that? Sure enough, yeah. So I want the absolute value of this mess. So here's something quick we can do, but it bears noticing. The stuff in here is all positive, because k is on its way to infinity. It's certainly much bigger than 0. Yeah, so these things are all positive numbers. The only negativity that could come out is from those guys, and that doesn't matter because we're talking about minus 1 to some power. I guess this would actually cause a negative sign, but it's okay because they're both gone. Any negatives can be eliminated from it. The other piece of simplification we can probably do is right here. 1 over k plus 1 factorial divided by 1 over k factorial. Just the thing I did when I was on the screencast. Instead of dividing by this, multiply by its reciprocal, you end up with 1 over k plus 1. So what we need to do is evaluate this limit now. K is going to infinity. K plus 1 to the k plus 1 over k to the k, and we had 1 over k plus 1 out of the factorial bits. Now, this is kind of cool that it leads us in this direction. You see, this is made up of a whole bunch of k plus 1s multiplied together. And then there's a k plus 1 down there. We could cancel 1 k plus 1 from the bottom with 1 k plus 1 from the top. And that will get us a really nice simplification. Let's see. That's going to make it be the limit. Again, k going to infinity. K plus 1 just to the kth power. We'll cancel one of those k plus 1s with what's downstairs. And we've got k to the k in the bottom. Well, that is equal to, you notice how the exponent is k in both of those? That's the limit with k going to infinity of k plus 1 over k to the k. So it's a little hard to think about. As we head away towards infinity, k plus 1 over k gets closer and closer to 1. So we're multiplying by a whole lot of things that are approaching 1. Effectively, the tail of that series, or the tail of that sequence, is 1's raised to the k power. But, you know, when we first start out, it's 2 over 1, and then 3 over 2. You start out with numbers that are bigger than 1, and how quickly do they approach 1? I don't know. Let's do a quick manipulation, though. This fraction in the inside the kth power there, that can be written as 1 plus 1 over k. Yeah, 1 plus 1 over k to the k power. And you might recognize that. Anybody? Well, if you do, good. And if you don't, I'll just tell you. That's the sort of Euler's first approach at getting the number e. Euler is spelled with an e, right? And he's the reason that we call that constant e. So, yeah, that's finite. We know the value of this thing. Probably should go prove that to you on the, or not, maybe prove is the wrong word, but convince you of that on a calculator, and then then you'll believe this part. And then what does the ratio test tell us here? It's finite, so the series is convergent. So we just saw that when we figured out the ratio of kth term to k plus, I said it wrong, k plus first term to kth term, and looked at that as k goes to infinity, we ended up with something that looked like this. It was 1 plus 1 over the variable. I'm going to use k. That's what I just did up here. I set k to be a variable, raised to the kth power. And of course, if I just type that, it's going to say, it's just going to echo that result, because it's just a symbolic expression. What I would like to do instead is have it print out the value of that for interesting values of k. So I'm going to use for k in, I don't want to look at this kind of thing, the range operator, because that begins with 0. So range 6, for instance, means 0 through 5. So I'm going to ask for k in 1, 2, 10. I think I'm remembering the syntax wrong. 1 dot dot 10. I think that's right. And what we're going to do, yeah, that's the right thing. What we're going to do, though, in this loop, is we're going to evaluate or print this as a decimal number. That's one quick way to coerce a thing to become decimal. Just multiply it by 1.0. Right. So you get 2. That's when k is 1, and then 2 1/4, or it's 9/4 if you want to think through how that would work out. We've got something 2.37. You see that the numbers are staying smaller than 3 at least. The 10th one is 2.593. Let's take this a little farther down the line, shall we? How about if we go from 90 to 100? 2.703, and down here. So it's getting closer to something, isn't it? It seems to be reasonably. How about 990 up to 1,000? 2.717. Well, I claimed before that this was E. Is it starting to sound like E? 2.718? Not that close yet, really. If I take this out another power of 10, there's 2.718, but still not that close to it. Keep throwing out powers of 10. 2.71827. Yeah, more closer, but still not quite there. But maybe you'll believe me at this point that the farther out we go in this sequence, the closer and closer we get to E. This is in fact the way E is defined. It's the ratio. It's the limiting value of 1 plus 1 over x as x goes raised to the x as x goes to infinity. But that sequence, that definition for E, is very slow to converge. So we have better ways of getting E that converge more rapidly, so you don't have to go out to the 100,000th term before you get a reasonable approximation. Anyway, that was the point. I wanted to convince you that the number that I got out there was indeed E, and hopefully it's something that you would recognize now. If not, well, maybe the next time you see it you will. So before we move on to looking at the root test, which is our other goal for today, I thought it would be nice to look at one scenario, which they happen to do it in the book, where the test is inconclusive. The one that we're looking at here is at the top of page 698. And it tries to analyze the harmonic series, 1 over k, where k is running from 1 to infinity. Now, if you look at the ratio of the k plus first to the kth term, and then take the limit as k goes to infinity, you have 1 over k plus 1 over 1 over k. Simplifying the fraction, you get k over k plus 1. But as k goes to infinity, that ratio gets closer and closer to 1. In fact, the limit is equal to 1. And that tells you the test is inconclusive. Now, that's kind of messed up because we know this series diverges, and it's the ratio test isn't going to help us on that, which is probably a good reason to look for more tests around. And the root test is kind of the next one. It's a notch more powerful than the ratio test, but it's also a notch more difficult to apply. One thing about it that is simpler is you don't have to look at successive terms, so a pair, the kth and the k plus first. You just look at the kth root of the kth term. Actually, I just lied there a little bit. Do you see how here it's written right here? The limit as k goes to infinity of the kth root of the absolute value of the kth term. Because these tests are, both the ratio and the root test, are really designed to tell you that the series converges absolutely, which is nice because if it converges absolutely, then of course it converges, period. And the fact that we can take an absolute value in here gets us away from having all the even-powered ones go undefined if a sub k is negative. Anyway, so what's the root test about? It's very similar. You look at a limiting value of something, but it's the kth root of the kth term in absolute values. And if you get a number less than 1 for that limit, then you've got absolute convergence. And if you get a number bigger than 1, divergence. And just like the ratio test, if you get 1, it's inconclusive. So why is it that these are the same outcomes, right? Actually, I think that's supposed to be a rho, a Greek letter that looks like P. But less than 1, greater than 1, equal to 1. Those were the same things we saw in the ratio test. Well, yeah, that bears some explaining. So if you're somewhere way down the line in the series at, say, a sub k, and you look at the kth root of that, you're going to get, well, approximately anyway, you're going to get rho, right? If this number is pretty large, you're on your way to this limit, and so yeah, it's equal to rho, or more, close enough to rho. Similarly, you can think about the k plus first root of the next term, a sub k plus 1. And that would also be approximately rho. So what happens if you raise both sides of these to the appropriate powers to kill off the radicals? This one leads you to, well, a sub k is approximately the rho to the kth power. And this one, we'd have to raise it to the k plus first power on each side. We get a sub k plus 1 is approximated by rho to the k plus 1. Okay, so that means your series looks like this: a1 plus a2 plus dot 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 up to, I guess that would be ak minus 1. And then the next terms, at least in approximation, can be thought of as rho to the k, rho to the k plus 1, etc. Right, so once again, we've got our initial part of the series, a partial sum, the k minus first partial sum, and then this tail. That means my dinner needs to come out of the oven. I'll be right back. Yeah, I'm back. Sorry for the interruption. So the point is that, again, the tail of the series can be treated as if it were a geometric thing, which, if that converges, if the series is to converge, this tail had better be a finite number. So we're doing the same analysis, looking at the tail, seeing it as powers, or a sequence of powers. Now, it doesn't start with the first power like it did in the ratio test. It starts with the kth power. But you can always factor let's say the tail looks like rho to the k power times 1 plus rho squared plus dot dot dot. So yeah, there's this factor of rho to the k, but all we care again about is whether it's finite. Yeah. So if this thing is supposed to be finite, then the part in parentheses had better be finite, and that's what we use to analyze it. Rho k is some particular value, some particular spot somewhere down the line, and rho to the kth power is a fixed number. So whether this is finite or infinite depends strictly on the part in parentheses there. Great. So let's try analyzing something using the ratio test. Darn it, the root test. Always speaking wrong. The root tests for the harmonic series, for instance, we know it diverges. Let's look at example. The series we're interested in is 1 over k, where k is running from 1 to infinity. So the root of a sub k, the kth root of a sub k, is equal to, Okay, the kth root of 1 over k. That's equal to 1 over the kth root of k. And can we figure out what happens as we take the limit? This is what rho is. Rho is equal to the limit as k goes to infinity of 1 over the kth root of k. Let me plug something into my calculator. Clear that junk out. The kth root is like the 1 over kth power. So what I'm interested in is k raised to the 1 over k. I'm going to have to use x because it's a graphing calculator and doesn't know nothing about no k's. X to the 1 divided by x. Well, let's take a look at that in a table. Why am I looking at 23 to start? I don't know why. Let's start it at 1 and look at the list. 1, that's the first root of, well, in other words, no root at all. That's 1. This is the square root of 2, then the cube root of 3, then the fourth root of 4. You notice how those numbers got bigger? In fact, it looks like this number peaked right there at 3 because it's getting smaller now. 3, 4, 3, 2, 2, 9. Oh, is it always going to be getting smaller? Wow. What do you think the limiting value of this is? You think it's 1? It sure looks like it's descending towards 1. I don't know. Let me change the table setup so we start out way down the line, about around the 200th term. Maybe not 2000th. 200th. Oh, we're still really just a little bit bigger than 1.02. What if I change it to the 500th? Oh, I did something wrong. Second table setup. I meant 500, not 5. Sorry about that. 1.0125. Okay, maybe I should go into the thousands. 1.0069. Yeah, it's starting to look like it's approaching 1, isn't it? Maybe that's something we could prove somehow or another. You know, well, okay, so that limit seems to be 1. That means the root test is inconclusive too. Darn it. Darn you, harmonic series. You're breaking all the rules. No, but still, the two tests together, the ratio test and the root test, usually will settle issues. The harmonic series is a bad case because it's right there, right on the verge of being convergent. If you change the exponent, it's a p series with p equal to 1. If you change that exponent just a smudge, it either diverges or converges. It's kind of the borderline between the two behaviors. I'm going to close out this video with one example about using the root test. This is example 2, part B. That's on page, did I really say that number right? No, 698. Sorry about that. Page 698 in the textbook. Just because I found this really interesting, I looked at this series and went, oh, well, that's going to converge because it's alternating and it's got k to the 10th down in the bottom, right? So you're going to have some ginormous numbers in the bottom. This has got to be going to 0. It's alternating. And the book said, no, it diverges. So I went and checked it out on the computer, right? And this is the data that I got. Here are the partial sums for various values of n. When n is 1, the actual just a single term in the sum, it's easy to figure out, you get -2. And then at 10, we get a number just a smidge less than -2. And then we got, at 50, we had a number even, well, a little bit less, but this is only a change in the third or second decimal place. But at or was it, at n equals 100, at n equals 100, it has become 8.16 times 10 to the 9th. I was amazed. So they're right, it does diverge. And after a second of reflection, I realized why. This numerator isn't just minus, negative to the k so that you get the alternation. It's also got 2 to the k. And which is bigger, 2 to the k or k to the 10? That's a good question, right? 2 to the k versus k to the 10. It seems at first like this would be, and if you try small values of k, yeah, it's not a big deal. When k is 2, 2 to the 10 is over 1,000. But when k is 2 here, it's 4. Not very impressive. But it doesn't take very long before the power of having the k in the exponent, and only a fixed number in the exponent here, takes control. Okay, so actually 2 to the k is much larger than here. Much larger than k to the 10. Cool. So in fact, the denominator ends up being way overpowered by the numerator, and well, yeah. But let's just apply the root test as we were supposed to, because really the example is about that. Okay, so the idea of the root test is we take the kth root of the absolute value of a sub k. And we don't care whether about the minus sign, right? The -2 thing. So what is the kth root of a sub k? Oh, one more thing to the test. We take the limit as k is going to infinity of that quantity. So for us, it's going to be the limit with k going to infinity of the kth root. I say k and write 5. I don't know what that's about. Kth root of, let's just call it 2 to the k over k to the 10. Well, what can we do with that? The kth root of something is like the 1 over kth power. So, and also if you're applying a power to a fraction, you can do it in both numerator and denominator separately. Yeah. So what we have is 2 to the k raised to the 1 over k. Something in my brain is trying to make 5s whenever I really mean to write a k. I don't know. Maybe I'm having a reaction to some. We got some very bad news today. One of my favorite mathematicians, John Conway, passed away today. Anyway, the bottom here has k to the 10 raised to the 1 over k. All right. So when you have a power to a power, you just multiply in the powers, and that means we get a 1 there. So the upper part of this is just 2. Let's think about what the rest of the limit is. This is 10 over k. This is k. Actually, let's do it this way. It's k to the 1 over k raised to the 10th. I'm just commuting the powers. 1 over k raised. I could multiply, and of course, if you can multiply, you can change the order. So that's fair too. Because we just recently saw what the limiting value of k to the k is. Excuse me, k to the 1 over k. We just did that, and that's 1. Right. So this limit is actually 2. So what does the root test tell us? If you've got this is our rho, right? That's the, I never said it, but rho is this thing we call the limit of the kth root of the kth term, and it's 2, and that's bigger than 1. So that tells us this guy diverges. So that's it for the ratio test and the root test. We'll see them a lot when we talk about power series, because they're our best tools for telling when a power series converges. But that's for Tuesday. Anyway, have a good day. I'll see you.